Hi guys, welcome to part 3 of When the Comparison Test Goes Crazy. So in this video, we're going to do 2 comparison test questions. They're going to be a little bit quicker than the ones in the previous 2 videos, and they'll be a little bit simpler as well. It's just that we're still going to have to think about how to pick that series for comparison. So in this question right here, I'm actually going to start off by applying the test for divergence. So my test for divergence, the limit as n approaches infinity of the nth root of 3 minus 1 is equal to the limit as n approaches infinity of 3 to the 1 over n minus 1. Well, 1 over infinity, that's as infinity, as we go to infinity, that's going to 0, and 3 to the 0 is going to 1. So this is just 1 minus 1 is equal to 0, and the test for divergence fails. Now you might think, oh, whatever, not a big deal. I can just take this thing right here and separate it. So I'll have n equals 1 to infinity of the nth root of 3 minus the sum n equals 1 to infinity of 1. Well, the problem here is that both of those things diverge by the test for divergence. That first limit is going to 1, and that second limit is going to 1. So they both diverge by the test for divergence, and we end up with diverges minus diverges, which we've seen we have to do something else to figure out. Remember, diverges minus diverges, it's kind of like the infinity minus infinity of series, and we know infinity minus infinity is an indeterminate form. So separation does not work here. Does not work because we get diverges minus diverges. So we need to pick something to compare to. And we know that our goal usually is to either compare to a p-series or a geometric series. Now just in this case, let's just point out that the integral test is really not a good test. We'd have to do the integral of that thing. The ratio test and the root test, it's not like I have everything to the power of n. The ratio test wouldn't be very straightforward here either. So neither of those tests is easy. So the comparison test is really our best bet. We know the integral test, we really only want to use if there are lns anyway. And I mean, there are no lns here, but also we saw that even if there are lns, sometimes it's not the best choice. So we're going to look at where we did the test for divergence and see how the nth root of 3 is the same thing as 3 to the 1 over n. I actually see the harmonic series inside this thing. So I'm going to try to compare to the harmonic series. Harmonic series, which we know diverges. So then the thing that I would want to be true is for the nth root of 3 minus 1 to be bigger than 1 over n. Well, that's just not extremely obvious, not evident, and the inequality is maybe not the easiest thing to solve either, so we're just going to go straight to the limit comparison test. We're just going to ignore figuring out if that's true or not. We're going to say, yuck, limit comparison test. So for the limit comparison test, it's actually really straightforward. So I'm going to have the limit as n goes to infinity of 3 to the 1 over n minus 1 divided by 1 over n. And when I plug in, I'm going to get 3 to the 0. So I'm going to get that 1 minus 1 on top, 1 over infinity on the bottom. That's going to give me a 0 as well. So I'm going to apply L'Hopital's rule here, HR, to get the limit as n approaches infinity of 3 to the 1 over n times the derivative of 1 over n, all divided by the derivative of 1 over n. Now notice I left it like that. I'm going to change it in just a second, but I want to point out something. I don't actually even need to know what that derivative is. It could be some crazy super hard derivative and that would be fine because it cancels out. I see that the derivative I have there on top and on the bottom are the same. Okay, so that said, I'm also going to need a ln 3 up here, and I am going to go back and we're actually going to find the derivative here. This will be negative 1 over n squared, negative 1 over n squared. And then these things right here cancel out, and this limit is approaching ln 3, which is bigger than 0 and finite. So by the limit comparison test, both series are doing the same thing. So what that means is we know the harmonic series diverges, so this thing right here diverges by comparison to the harmonic series. Okay, so I want to go back to the fact that those two derivatives there canceled out. That 1 over n prime canceled out with the 1 over n prime on the bottom. That in and of itself is one of the reasons why picking the series 1 over n was a really good idea, because we're like foreseeing the limit comparison test in the future and being like, hey, that 1 over n, I'm going to have to take the derivative of it using a chain rule. So with that in mind, let's use that thought for the next series that we're going to do here. So we're going to have n equals 1 to infinity of sine of 1 over e to the n. Actually, yeah, 1 over e to the n. So again, the test for divergence fails because I get the limit, n goes to infinity, sine 1 over e to the n. Well, 1 over e to the n is going to 0 as n goes to infinity, and sine of 0 is just 0. So what I see here, though, is on the inside, I have 1 over e to the n. That's a geometric series. I have that geometric series inside there. So if we're like doing the same thing in the last one and foreseeing the limit comparison test in the future, we're like, oh, hey, those derivatives might cancel out when I do L'Hopital's rule, making this easy. So we're going to immediately compare to the sum n equals 1 to infinity of 1 over e to the n, which is a geometric series. My r is equal to 1 over e. The absolute value of r is less than 1, so it converges. So what I would want to be true is that sine of 1 over e to the n should be less than 1 over e to the n. Again, this is just not clear at all. Having that sign there does not make this easy, so not evident. And we're going to move straight on to the limit comparison test. And that limit comparison test, again, was a really good reason to pick 1 over e to the n as our series of comparison, because what's going to happen? I'm going to have the limit as n approaches infinity of sine of 1 over e to the n divided by 1 over e to the n. And I'm going to get a 0 over 0 here, which means that I can apply L'Hopital's rule. So I'll do that. And when I'm applying L'Hopital's rule, that chain rule on the top, so I'll have cosine of 1 over e to the n, that chain rule on the top is going to have me pull out the derivative of 1 over e to the n. So that's the same thing as e to the negative n. This is negative e to the negative n, divided by the derivative of the same thing. So those derivatives are going to cancel out, yay chain rule, yay L'Hopital's rule. And now when I plug in, the inside is still going to 0, but now it's cosine 0, which gives me a 1, which is bigger than 0 and finite. So by the limit comparison test, both are doing the same thing, both series. So in other words, the sum n equals 1 to infinity of sine of 1 over e to the n converges by comparison to the geometric series n equals 1 to infinity 1 over e to the n. And that is all. All right, hopefully that this has been helpful in helping you to think about how comparison works and how to pick your series for comparison. That's all. Bye, guys.